This is the 37th video in a series on single agent search, and today we're going to continue to look at heuristics and polynomial domains, and particularly we're going to continue to look at true distance heuristics, and the particular one will be these Euclidean embeddings, also differential heuristics. So a bunch of names distinguishing what's going on here, but in particular we're going to look at compression. So we're going to look at how we compress differential heuristics. And one of the reasons why we're going to look at this today, I mean, there's many different things we could choose to look at here, is that this gives us a parallel to what we looked at in pattern databases. In pattern databases, we compress them by grouping together states and storing the minimum of them. And we've already seen that when we group states together and take the minimum of them by building an abstraction, which works well in pattern databases, that it doesn't work in polynomial domains. And so if you were to try to do something about this that's similar to group states together, we would tend to also have some loss in our heuristic values. But what we're going to do instead is, or we're going to do that in a certain way, but we're not, instead of trying to group states and store the minimum, we're going to throw out some of the values, and then we're going to try and use interpolation to interpolate back the information that is missing. And so the idea here is that, so we're going to think about one heuristic, and of course we can do this across multiple heuristics. And I'll talk a little bit, I mentioned it at the end of the previous video, but I'll talk a little bit here about sort of the choices when we do this sort of compression. But let's look at sort of a picture that we have of what is going on. And so the idea, so let's look at a high level, right? So if you remember last time we were looking at this being the all pair shortest path data, and we had sort of all end states here, we had all end states here, and the traditional differential heuristic is basically saying, look, I'm going to take some row here, and I'm going to store that row, and I'm not going to, and I'm compressing, in some ways I'm compressing the all pair shortest path data by not storing any other row. And what we're going to do here is we're actually going to do something that's similar to this, except that we're going to basically store only part of the data in one particular row. And so we end up in one row, we're not even going to store all the data in here. So this is going to be our DH compression. So this is a regular differential heuristic. This is a differential heuristic that's been compressed. Okay. And this is going to be particularly useful for low memory applications. And the other thing is that we can compute one of these very, very quickly. And we can, like in one or two searches, we can do one or two breadth first searches through, or uniform cost searches through a problem, and immediately have a fairly good heuristic. And then if we even need less memory than that, we can do this fairly quickly. So this is looking at, again, not the large road network types of scenarios, but maybe something that's more of a dynamic problem that's changing, and that we maybe have very limited memory because we're deploying on a mobile device or something like this. Or for instance, in the context of a game, most of the memory is being used for assets that are within the game, for the art and sound and other things like that. Okay, so this is the idea. I've said the idea is that we're going to only store some of the data here, but there's obviously some details of how this could possibly be done. And so let's talk through a little bit about this. If we think about this within a state space, and I'm sort of going to draw a map here. So right, this is the all pair shortest path over here, but now let's sort of look at this as a map here. And I'm going to make it just be a relatively simple map here for the simplicity of my own calculations. And if you think about this, let's sort of imagine a very simple scenario here, where essentially what we're going to do is we're going to imagine that we have the heuristic everywhere, or we could imagine having the heuristic everywhere, but you could imagine, so that's just to be really simple about it, that if I do something like this, where I'm sort of keeping every other state. I'm basically have little gaps here where I don't have states inside my heuristic. So I can sort of have some pattern. It's sort of going to be like a checkerboard pattern where I have some values that are missing. So if I just sort of continue to draw this through the entire state space, you could imagine I do something like this. And, you know, there are these states, these white states where I have no heuristic information. And there are then these dark states where I do have heuristic information. And you could just imagine as we search, basically on some states we'd get no heuristic, and other states we would get a heuristic. And if we're able to interpolate between our heuristic values, then we might be okay, and we might be able to tolerate the loss like this. But let's go through. That's sort of again at a very high level here. We might actually be able to be more sparse than this in practice. But if we're thinking about this idea is that we're going to have some places where, okay, so let's go a little bit more detail. What are the black states? The black states are, we have some pivot. So there is going to be some pivot here. Maybe this is my pivot. And a black state means that we know the distance from pivot to x, or x sub I, whatever state that happens to be. And maybe let's call this s of I. So the ith state, whatever one it happens to be. And white is we do not know the distance from the pivot to s of I. Okay. So the idea is now when I want to compute a heuristic between two states, then sometimes I'll be able to compute it and sometimes I won't, because I've thrown away a bunch of that information with the hope that I would be able to recover it later. Now, there's a couple caveats to this that might make this a little bit harder than what you think. So if my goal is one of these states that is actually being stored here, so it's one of these black states, then when I want to do a heuristic calculation, so what happens? H between A and B that we're going to do here is just going to be simply the absolute value of the distance from A to P of I, and minus the distance from B to P of I. I believe in the other one I wrote this, may have written P of I to A, but since we're assuming an undirected graph still, I can write these in any order, and so we don't have to worry about that. So I write it as something like this, and so let's say that B is the goal and the B is fixed, then I'll always know what this value is. And then on some states I'll know this, and other states I won't know this, and we would just get a heuristic. In the places where we know it, we get a large heuristic value, and in the places, well, hopefully a large heuristic value. In the places where we don't know it, we won't get a large heuristic value. In fact, we'll get a heuristic of 0 because this will be a question mark, and so we'll really just say, well, we could be 0, wait, we don't know. And we can tolerate in that some sense. So if you remember, we talked about so this would be an inconsistent heuristic once we do this compression. And we know that one of the techniques we can use to deal with inconsistency is we can use a bidirectional path max. And essentially that would allow us to take a heuristic that we have at some state, which might be large, and propagate it to a neighboring state, which has a heuristic of 0, and we would still get a reasonable heuristic value in these blank spaces. And I'm going to show, in just a minute, I'm going to show some pictures that sort of walk through this process. I spent some time animating this back actually quite a few years ago now, but we'll go through some of those animations because I think they're helpful in understanding what happens here. But there's a second case here. So there's one case which is if this is the pivot. So if the goal has a stored distance to the pivot, then it just means that sometimes we don't know a heuristic value. Okay, but because in these sorts of problems, one of the things, I actually didn't mention this in the previous lectures, but in a polynomial domain, we tend to be looking at all possible, we have anything could be the start state or anything could be the goal state. If you could imagine like in an exponential problem where or an example of an exponential problem is like we've got a bunch of trucks, they're going to deliver a bunch of packages. At the end of the day, all the trucks are back in the depot. So we have these goal states that are very well known. And I wouldn't want to know to get necessarily between some arbitrary state. I mean, you could still do this, but you may not want some arbitrary state where you've got a bunch of trucks with a bunch of packages in them, and you want to know the distance to another state with a bunch of trucks with a bunch of different packages in them. Like that may not be a query that we're as interested in. We still may be interested in it, but in like there's less need for that in exponential domains. They tend to have goal states that have more overlap to them. Whereas in something like a polynomial domain, if we think about pathfinding in a game or in a road network trying to get around, we tend to want to go from some arbitrary location to some other location. We go to somebody's house that we've never been to before, or we're going between stores. So we really need to be able to answer queries between any two arbitrary states. And so now the problem is we can't guarantee that the pivot, so if the goal has a stored distance to the pivot, then we're fine because I can always do this calculation. But if the goal doesn't have a stored distance to the pivot, if the goal is on one of these states where I have unknown distance, then I will never know what the distance is from the goal state. If B is the goal, I'll never know what this distance is, and I'll actually never be able to do this calculation. And so what we end up with here is like I can never actually compute a heuristic value for those states. And so that's a problem because now we have a heuristic that for a particular problem, I can actually never use that. But it ends up that actually there's a way to handle this. So this is the first case that we looked at. If the goal has stored distance, let me just put it here. If the goal has stored distance to the pivot, then sometimes we don't know the heuristic. If the goal does not have stored distance, then we never have an actual distance here. The actual distance to the goal. Okay, and so we're going to need to be able to compensate for that. And let me just say for a minute, I didn't say this again earlier, so like we can think about some pattern like this. The idea of this pattern, right? So in this pattern, we've thrown out of every 9 states, we've thrown out every one of them. But generally speaking, what we can do is we can basically say, look, I have a number of states here. They all have some value on them. And basically I can say, for all the states modulo 7, if it's equal to 0, then I'm going to keep the state. And if it's not equal to 0, then I'm going to throw it out. So that would throw out 6 out of every 7 states. And it's not going to end up with a pattern that looks like this. It'll be much more sparse, but this is the type of thing we would do. So we come up with some function that says, keep the states that match this function. Modulo would be a very useful and a very common choice to make. And that would allow, would give us some pattern here of states that are kept versus not kept. We could be looking at like keep the even rows and throw away the odd rows. So you could be looking at the X and Y coordinates and deciding which ones you want to throw out there. And so that might be like, that might give us a 50% compression if we think about, keeping every other row. So it's things like this that we would do to just say, throw away all of those values, right? So the white values are all thrown away. There's a very easy way to do that algorithmically. We just, it's this computation that says these values are stored and they're not. And so again, if we look at state up and both the start and the goal are stored, we can look it up. If the goal has stored distance, but the start doesn't, then when the start doesn't, sometimes we won't know the heuristic. If the goal doesn't have a stored distance, then we're going to have to do something else to get the distance here. And the idea here is, and let me make this in another color to make it very obvious. So let's suppose that this is my goal right here. And the idea here is that, well, I don't know the distance to the goal, but I can choose another state nearby here, and I actually can just do another level of approximation. And so we're going to call that, we have this state here that's going to act as if it's the goal. So I could call this like G prime. So it's like a surrogate for the goal. And the idea is that what I want to do is if I don't have a distance to the goal, I'm going to compute the distance to this G prime. And then what I'm going to do is I'm going to say, well, this state this G prime state is only one step away from the goal. And therefore, I can take the heuristic to the goal, whatever it happens to be, and I can just interpolate, well, I'm only one step away here, so the heuristic at most can be off by 1. So I take the heuristic value to this state where I do have a distance, and then I subtract 1 from it to get the distance to here. So what happens here, in this case, I'll write this in a color, so what we're going to do is we're going to use, as a heuristic, we have some surrogate for the goal. So I want HAB, and what I'm going to do is I'm computing. Now, I have distances to the pivot, but I don't necessarily have them everywhere. So if I have it, I'm going to do distance of A to the pivot. And then what I'm going to do here is distance of B prime to the pivot. In this case, B prime, if I'm using the same notation, so this is the surrogate goal. Okay, so B prime, so I'm going to use the distance to those, and then because I'm going to subtract the distance from B prime to B. Okay, so the idea here is I'm going to choose some other state, which is going to act where I do know distances. I'm going to compute the heuristic to that state and then subtract the distance between that state and the goal in order to get an actual heuristic here. And actually, there may be multiple states that we could use here as surrogates for the goal. And it ends up that if you use multiple ones, then you might actually be able to offset the loss that you get. So right, if I think about going this direction, then computing the distance to here is actually going to be very accurate. If I think I'm searching from over here, then using a surrogate that is over here, basically I get a heuristic that is 1 too far to this state, and then I subtract 1, and I actually still get the same heuristic value that I had before. So we can, in the same way that we use multiple pivots to increase our heuristic values overall, we can actually use multiple of these sort of surrogate states here that sit in the place of the goal, and then we compute the distance to those for each time I do this computation. I'm going to basically I could use one or more of these surrogate locations. And what happens is that, so I'm solving a particular problem. I have a goal, and I basically, once I look up the goal, I say if the goal is not a state that we don't have an actual distance stored, we'll do a backward search until we find some number of these surrogate goals that I can use where I do have heuristic information, and then I'll use those states at runtime. I do that calculation once, a little reverse search, and then I do my forward search, and I can just compute this over and over again during my actual search, and I don't need to redo this reverse search in here that is looking to see where I can actually compute my heuristic values. Okay, so this is the high-level idea, and I'm just going to walk through here a presentation that shows some of these steps that hopefully will help make this a little bit clearer. Okay, so the first thing we'll look at is the single source shortest path. So here we're thinking about a pivot, which is on the left-hand side. It's red with yellow in the middle, and that's where it's in the dark blue. And what we see here is for that particular pivot, the yellow states, because they're both the same color, they'll have a heuristic of 0 between them. So using a single pivot here is going to impact the where we get good heuristics and where we get bad heuristics. And so generally speaking, the idea is we would want to use multiple pivots. By using multiple pivots, we get good heuristics in different places. So here, these the two states on the right that are both red, they have a heuristic of 0 between them. But if I choose a different pivot, now they're actually going to have a very good heuristic. And it's the states at the top and the bottom that will have a heuristic of 0 between them. Okay, and those states actually still have a heuristic of 0 between them on both of these problems. And so then in theory, you'd want to have a third state here, a third pivot that would then capture these states. And then you'd capture most of the distances in this map. Okay, and so what we're going to do here is, because we want to store multiple of these pivots, but we want to do it using less space, is, as I said, we're going to throw out most of the values. So here what I've done is I've drawn the map with 0 values everywhere, except for the except for the places where I keep the heuristic, which is then showing these colors. And these are the exact same colors as we saw before. So this is the first heuristic, where, again, the red states are would have a 0 heuristic between them. But we'd like to basically use the combination of these heuristics. But any two states that are white then have no heuristic at all. And if we zoom in here, the idea is if my goal, so my goal is in this area over here, and essentially this is what I was describing. This yellow region would be a region that we do a backward search. We do a backward search to find these states here, and that when I want to search into that state, because we don't have a heuristic at the goal, for if the goal state is exactly where the arrow points, then we'd only have it at these neighboring red locations. So we would just say, look, well, these neighboring red locations, we're going to treat them as the goal. And then what we're going to do is we're going to compute the heuristic to the neighboring states and then subtract the distance from the states to the goal there. And the start state, sorry, is over here where we do happen to have a heuristic. And now I'm just going to show you, I have some nice animations here, is that we're going to show you what happens when we just apply this in a naive way. So the idea here is we've built this heuristic, we've compressed it by throwing away a bunch of the data. And the idea is I have multiple sets of this data that have different heuristics that are good in different places. And so interleaved right next to each other will be a bunch of different heuristics that all have distances to different pivots. And so what happens is we can start to search here. So again, this is the start and this is the goal. So same sort of instance as before. And if we just search with A star, and this is with a straight line heuristic, then we just sort of search in all directions because the heuristic is very weak, because it doesn't know that it looks like we're very close to the goal, but we're actually very far. And so eventually we do make it to the goal and we solve this problem. But if we search using this compressed heuristic, well, we actually see something really funny happening here. So before, what we saw is this very clear distinction between the closed list in red and the open list in green. The open list was basically surrounding the closed list, and the closed list, was sort of expanding outwards. But here we don't see that. And what's going on here is that some of the heuristics have very poor heuristic values for the particular goal state we're looking at, and therefore they have very low F values, and therefore we want to expand all those states first. So those are all the red states here. We would go out and expand them all. And some states have really high values coming from a different pivot. And so those are the green states. Since they have high heuristic values, we don't want to expand them. And that's coming really from the inconsistency. So at this point, we've explored a lot of the state space, but of what we've explored, we've actually only explored about half of those states because the other half had really high heuristic values. So we have an inconsistent heuristic that we can have very high values next to very low values. And if we just run A star, continue to run A star here, we know there could be, the values here don't grow exponentially, but there could be a polynomial number of re-expansions. And so if we see here, this is where the heuristic values are. These heuristic values, just to show this one more time, they correspond exactly to the sort of the high and low regions in the state space. And so these good heuristic values basically prevent us from expanding a bunch of states. But eventually our F cost gets up and we'll start to explore these states. And then what happens is when we continue the search, so this is just another picture. There's very low heuristic values with very high heuristic values next to them. And we're just going to search in between them. So what you're going to see now here is we're going to start re-expanding states. So all these states that are turning purple are all ones that are being re-expanded, and we're going to go through. If we find like a one-step shorter path, we expand it, and then we find another one-step shorter path, and we expand it, and we just repeat this process over and over again of shortening the paths, and this actually becomes very, very expensive. So the heuristic here, although it's a more informed heuristic overall, the fact that it's informed in some places and not informed in other places means that actually does a lot more work than the baseline heuristic. However, as we covered a few lectures ago, we learned about Bpmx, and Bpmx basically allows us to say, take these high heuristic values and propagate them to your neighboring states. So all these 10s become 19 because they're neighbors of states with a heuristic of 20. And now if we go back to the same instance and we search with Bpmx enabled, we still, because of inconsistency, may do some re-expansions, which are the purple states here. But practically speaking, you can see the search basically goes straight from the start to the goal. So this heuristic is very powerful. It allows us to solve this problem much more effectively. And if we just were not to compress it at all, we would do maybe even fewer states than this. We wouldn't see any of these purple states here. We would just do a regular search with a consistent heuristic. But when we compress the heuristic, then, and this is getting into what's important here, by compressing the heuristic, we can either take a very strong heuristic and just use a lot less memory to search with it, so we can get almost the same results using a lot less memory, or we can have a lot more heuristics, so we get a diversity of heuristic values, so we're more likely to have a very strong heuristic somewhere nearby. And so having a strong heuristic nearby, I'm more likely then to get those heuristics. So with a better diversity of heuristics, I can get better results overall. So this is what goes on in practice when we do this, and hopefully this is a useful picture. Just transfer back here. So the idea, just to again give an overview here, is that what we're doing is we are able to take, instead of storing everything, a single source shortest path from a single pivot, and have every single value stored, we can just choose to store some fraction of those states. And when we store some fraction of these states, a small value, there's basically going to be a bunch of states where I don't know distances anymore. So when I go to do this computation, I may not know the heuristic of, for A, I may not know the distance, or for B, I may not know the distance. And what we said is, look, if we assume that B is the goal, if I don't know this for A, it's not really a problem, because sometimes we don't know it, sometimes we do, and so but at least we'll be able to get the heuristic most of the time. And as long as we use bidirectional pathmax, we can basically recover the heuristic in these places that it was lost. And by recovering the heuristic in the place that it's lost, then we basically, we'll mostly be able to recover that. The problem is that if the goal is not stored, then I'll never be able to actually do this lookup. And so that's more problematic. And so in this case, because this distance here is going to be needed over and over again, what we're going to do is, given a goal, we're going to do a backward search until we find some states that we can use as potential goals. And for those, what we can do is we can say, well, the heuristic, basically I'm going to store this distance from that state to the actual goal. And when I want to compute a heuristic to the goal, I'm going to compute the heuristic to this sort of surrogate goal and then subtract this distance to try and recover, well, it will recover an admissible heuristic to the actual goal. So this is almost like the triangle inequality being applied a second time again here, given that we just get using a secondary goal. And so what we can see here is, if we now start to put together these pieces that we've learned, which is we need to use true distance values in polynomial state spaces to be able to preserve distances, or be able to preserve good heuristic values. That not only dictated that we built these true distance heuristics, so differential heuristics are one example, but it also dictated that as we compress them, instead of grouping states together and keeping the minimum, we're actually going to preserve the actual distances, because that's what's stored in here, actual distances. And then we're going to use interpolation of real distances here. This is sort of our interpolation factor to be able to recover the distances that were lost. And this compression, again, results in an inconsistent heuristic. And here it's very important that we try to recover the heuristic value locally with local propagations using bidirectional pathmax. And so this is the compressed differential heuristic. And this allows us to store our heuristics using less information. Either we use less storage to store them, or we can get a larger diversity of values, which then would give us better performance. Okay, and so this is going to complete the differential heuristics, but in the next lecture, in the next video, what we'll be doing is we'll be looking at how we can interpret these not as these sort of just one-dimensional single source shortest paths, but we'll be looking at how we can view this problem more generally as an embedding in a Euclidean state space. And so again, hopefully we'll see you in the next lecture.